Support for this grassroots community television program comes from U.S. Trust. From wealth structuring to investment management, U.S. Trust's global perspective, unique team approach, fiduciary platform, and more than 200 years of experience provide for the kind of insights, solutions, and expertise that have a worth all their own.
Hi, good evening. It's a pleasure for me to welcome you to this evening Heinz Pagel's Memorial Lecture, sponsored by the Aspen Center for Physics. My name is Enrico Ramirez-Ruiz. As you can probably tell, I'm not from Aspen. I'm actually from Santa Cruz. We really thank you for embracing all these physicists that come and invade your community in the summer. I think we're easy to recognize, so we thank you for embracing us and for having patience with us. So it's really an honor for me to introduce today's speaker, but before I do so, for those of you that don't know what we do at the Aspen Center for Physics, I'm a general member of the Aspen Center, and I'm here to represent us. The Aspen Center is sort of like summer camp for physicists. You probably see bumper stickers at Aspen that says, I'd rather be skiing, or if you're from Santa Cruz like I am, I'd rather be surfing. Well, if you're a physicist, I'd rather be in Aspen, because they basically take away all of your responsibilities. Not that we don't love students, but we do. But, we come here, we get to concentrate for a period of 15 weeks. We're about 500 physicists that come. We get to do it for periods of 3 weeks at a time. And we're just basically free to think and interact with each other, which is, an amazing privilege. So we are extremely lucky to have the Aspen Center and to be part of it. And we're also very grateful that you accept us in your community. Well, it's a real honor for me to introduce Bob to you. As you all have here, you have his biography, which is really impressive. I mean, I think if he was a general, he would just be completely covered with medals. At every stage of his career, he's basically been rewarded by the amazing work that he's done. He's really one of the best astronomers alive today. There's something important that I wanted to share with you. One of my favorite physicists, which is Niels Bohr, used to say that really the measure of a great physicist is not only the work that you do, but whether or not you're able to enable the next generation to do great work. And I think in that category, Bob is just basically the best. Why? Because 2 of his grad students actually got the Nobel Prize. So you can imagine the other grad students that did not choose that project. What are they thinking now? But that just tells you about the human quality and the scientific quality of Bob. And I'm sure he's going to give us an amazing talk, and it's a great pleasure to have him here. Thank you, Bob.
Thank you. Thank you for that wonderful introduction. It makes me very eager to hear what I have to say. What I want to do today is tell you the history of the universe, which is about 14 billion years, in 40 minutes. And to do that, I have to leave out something. And I have found the most effective way to do this is to leave out the reference to work of others. And so those of you from the Aspen Center for Physics who have come here tonight with the hope that I might mention your work, too bad. I'm in a hurry. What I want to talk about is the use of supernovae, which are exploding stars. And you can see one in this picture down here. You see that one star down there, which is, for a little while, as bright as about 4 billion stars like the sun, and very nearly as bright as a whole galaxy of stars. And these supernovae turn out to be useful as a kind of yardstick to measure distances in the universe. We can also measure velocities in the universe. And that means we can figure out, in a way I'll describe, how the universe has been changing over time, how the expansion of the universe has been changing over time. We expected to find it decelerating, slowing down due to the presence of matter. But what we find is that it is accelerating, speeding up. Interestingly enough, Einstein had an idea back at the beginning of the 1900s about how gravity might work on the big scale. And his idea was that the universe was static, and he invented something that was a kind of anti-gravity term to do that. As we'll see, he abandoned that, but we're back to something like what the thing that people call Einstein's blunder. Now we've undone it, and we've used that. We've been diving in Einstein's dumpster and smoothing out his crumpled up sheets of paper, the way people do, I've noticed, over there. I think they are mostly bears behind the Aspen Center for Physics. Okay, so the astronomical phenomenon that I want to talk about is supernova explosions, and then I'll show how they've been used to measure the distances in the universe. So I want to show you a kind of speeded up story of what a supernova explosion does. The supernova, the star, explodes, blows itself to smithereens, and it emits light that for a month or so makes it rival the light from a galaxy. And it is literally the death of a star, and in this metaphorical way, it makes you think a little bit about the fact that human life is quite short compared to the cosmic life. And so I want to take a moment here to digress in an important way and to recognize someone who lived in Aspen, who was important to the Aspen Center for Physics, and was important to me personally, and that's Sterling Colgate, who died last year. And Sterling had a very interesting career that spanned a lot of fields. I don't have time to tell you about all of this, but he's a man who did not live life by halves, who threw himself entirely into whatever it was that he was engaged in. And I thought it would be appropriate because there was a very nice documentary film, a NOVA film, made in 1988 about the supernova that we saw in 1987, one of the brightest supernova in the last 400 years. This documentary has a few little clips of Sterling, and it shows the ideas that drove him. So I thought I would digress for a minute and say a few things about Sterling, really to let him say a few things himself. Now, I'm not too slick at all this, but I'm going to get it. Okay, here we go. So this is just a little clip. First I plug in the sound. I knew there was some reason. Okay, here we go. There's Sterling.
An extraordinary intuitive physicist, Colgate was the chief test scientist for the hydrogen bomb program at the early age of 27. Then in the 1960s, he became fascinated by still larger explosions, exploding stars.
I want to know why the dangers blew up, and then why they kept on shining, and then really more than that, I want to understand how they blew up. In other words, once you know the mechanism, what was the distribution of matter when they blew up? And the first problem was that, when we put in the thermonuclear fuel, that is, mocked it up in a computer calculation, we'd get a big explosion inside, but then it would go out of ways and fall back in again. It would always collapse. And it was the biggest puzzle to figure out how in the world you could get these things, as we saw them in the universe, regularly explode, and yet the calculation showed they collapsed. The exciting thing about this supernova down in the Magellanic Cloud is that we may be able to tie down all of these things, how it explodes, how it shines afterwards.
All right, so that's one little clip where he wants to know why the damn thing blows up. That's good. It turns out that one of the important predictions of that type of model was that when the star explodes, the real mechanism was a collapse at its core, which would lead to the emission of a vast hail of particles, so-called neutrinos, which are massless, chargeless, but they do carry energy and they can be detected. And for this very nearby supernova in 1987, the neutrinos were seen for the first time. And I want to just show you the little bit in this of Sterling's reaction to the discovery of the neutrinos and the validation of this theoretical picture that he'd been working on for about 20 years before that. Now let me see if I can just do this. Here he is. Whoops. Okay. First we'll see the Japanese scientist.
Outside solar system.
While the experimenters were pleased, the theorists were ecstatic.
I was just far out, man. When I heard when I heard from the supernova that there were neutrinos, and that this, this theory of so many years in a lifetime was suddenly out there, oh my God, what a trip, man. What a real trip. It was just, these neutrinos, oh, can't do anymore.
We all talk like that. And then just one last little bit more. One last little bit more. This is at a conference held in Washington where there was the results about the neutrinos were known, and here are some of the folks discussing the story of the neutrinos and how it affected our understanding of the supernovae.
We understand these things. I can't believe it because, damn it, this whole house of cards gets built up,
Present were Sterling Colgate, Nobel Prize winner Willie Fowler, and Fred Reines, whose American-based collaboration also detected neutrinos from the supernova.
We have a chance to actually do some experimental observational work and check up on all the theories of these young guys.
Wait till we get one in this galaxy, though. I can taste it.
This is close enough for me.
Oh, no, you just see that thing, those neutrinos go ka-chunk, ka-chunk, ka-chunk.
Neutrinos were not the sole topic of conversation. There were rumors that Bob Kirshner had finally changed his mind about the progenitor star.
Oh, never mind that part. So I thought that was awfully good. It showed you the enthusiasm that Sterling brought to the whole subject, the passion for it. He did not do things by halves, that's for sure. And I like the part where he says about he could taste neutrinos. For the insiders, of course, this anticipated the various flavors of neutrinos that we've been interested in. Now, let me return to my main topic. But Sterling is a wonderful man, and he contributed a lot to our field. He contributed a lot to the Aspen Center for Physics, and I learned a lot from him, too. Okay, but I want to return to my subject. Here is the supernova 1987A. That was the subject of those remarkable expressions of joy. It was just far out, man. And this is an image of the supernovas taken many years later with the Hubble Space Telescope. And these supernovae are very interesting objects because they are so bright. It turns out that there's a class of them, which I'll talk about, which is very nearly the same brightness. And because they have a narrow range of brightness, we're able to use them as yardsticks in the universe. So let's get going. Where are we in the universe? At the time when Einstein started thinking about the universe, which was about 1900, 1915, the Milky Way galaxy, which this is a representation, an image, was what people thought was the whole universe. So that's quite different from our conception today, of course. The sun is one star in this assembly of 100 billion stars, more or less like the sun. You can see that there's dust in it, there's gas, glowing gas, this pink stuff is glowing gas. And there are also a few other little fuzzy things in the sky. And they turn out to be the most important things in this story. So for example, over here, there's a little fuzzy thing, which in the parlance of the time they called a nebula, but which today we know, and I'll show you how we know, is another galaxy like our own Milky Way, and that the universe is not made up of the stars of our Milky Way galaxy. The universe is made up of galaxies like the Milky Way, plus many invisible ingredients which we know about, but which we cannot see. So let me say more about that. Well, speaking of things that you cannot see, here's Einstein in this era, and of course this was the era of photographic plates as the medium for recording light. Today we use silicon detectors, electronic detectors, but if you look at this one, you can see, for example, that while the shutter was open, which must have been quite some time, this person got up and left. This person shook his head, disagrees with Einstein. The most interesting thing is that we now have a way of processing these plates so that we can see what people were thinking. And what he was thinking was, it must be static. That is, Einstein thought that the universe, Milky Way, would not be either expanding or contracting. And he made a particular solution to his equations of general relativity that did just that. And to do it, he put in by hand an extra term, the so-called cosmological term. So the reason he did it was not because of some philosophical notion, although that might have been somewhere in the back. What he said was, that term is necessary only for the purpose of making possible a quasi-static distribution of matter as required by the fact of the small velocities of the stars. And so it was the measurement of the stars that led him, at least that's what he said, to make this particular solution. In the land of algebra, we use the Greek letter lambda to stand in for this cosmological constant, this anti-gravity thing that Einstein invented to push back against gravity and to make the universe static. Okay, so how have things changed? Well, astronomers learned fairly quickly to map out our location in the Milky Way. So shortly after the beginning of the 20th century, we found that our location in the Milky Way galaxy is not at the center. We're out at the edge, something like this. This is a picture of another galaxy, and so we're out there, far from the hub, which is the name for another place, in the center. And our view has been one of constant demotion, of course. We used to think that the Earth was at the center of the universe. Then we said, okay, it's not the Earth, we're going around the sun, but many people might have thought the sun was at the center of things. And all this showed is that once more we were demoted out to the outskirts of the Milky Way galaxy. We're not at the center of the galaxy in which we live. Now, the ability to make measurements, of course, is an important thing. And one thing that we've been able to measure is the size of the Milky Way galaxy. People knew this back in the era that I'm talking about pretty accurately. And it turns out that astronomers use a unit of distance that is a little peculiar. We use the unit light year, which is the distance that light travels in a year. It's more comprehensible, maybe, if you think about the light foot. A foot is a unit of distance that's used in the United States and in Myanmar, which is about that big. And it takes light a nanosecond, a billionth of a second, to travel 1 foot. So when you see the world, you don't see the world as it is at this instant. You see the world as it was at the instant when the light bounced off the object that you're looking at. So, for example, I'm looking at people up in the front row. I don't see you as you are. I see you as you were 15 nanoseconds ago. Curiously, the people in the back of the room appear younger. I see them as they were 72 nanoseconds ago. Okay, just a humorous remark in a room like this, but in astronomy, it's no joke. The time that the light takes to get to you is an important aspect of your ability to understand the world. And it's an advantage, because it means when you go out at night and you look at the stars, you see stars whose light was emitted when the Federalists controlled both houses of Congress. It's quite interesting. Or when before there was a United States Congress. You can see light that has traveled for 10 years from nearby stars, 100 years from medium distance stars, and there are many stars whose distances are 1,000 light years away that you can see at night. Now, these little fuzzy things, these nebulae, these galaxies, turn out to be something else. They are not stars in our Milky Way galaxy. It turns out, and I'll show you the evidence, that they are systems of stars like the Milky Way, but located at great distances, 1,000 times farther away than the distances inside the Milky Way. So they are at millions of light years. Even the nearest ones are millions of light years away. The way we know that is by making observations with telescopes, the most advanced telescopes of the era, This is the 100-inch telescope at Mount Wilson, which was the leader in its era. And again, the most important thing in the observatory is kind of inconspicuous. It's the observer who sits up on that bent wood chair. At this telescope, the most famous observer who sat in that chair and took photographs with the telescope was Edwin Hubble, who's shown here in this somewhat overly dramatic photograph. And here's here's his picture of a nearby galaxy, the Andromeda Galaxy, which you can see without a telescope in the fall from a dark place like Aspen. And it's a fuzzy patch of stars like the ones I've showed you before. And you can see that he's marked on here some of these stars. There's one up at the top there. He was looking for novae, a kind of exploding star of a kind of medium strength explosion. But then he crossed that out and he said, no, I guess I saw this one before. It's a variable star. And so he found a variable star, which he thought was in this galaxy on the 6th of October in 1923. And it turns out that that star is like stars that another astronomer, Henrietta Leavitt, at the Harvard Observatories had studied, and where by studying the properties of the star, you can figure out how bright it is. By measuring how bright it appears, you can infer how distant the object is. And in this case, it was that the distance was much bigger than any distance in our galaxy. It was a distance on the order of 1 million light years. My story tonight is about using stars to measure distances. Only the stars I'm going to talk about are 1 million times brighter than Henrietta Leavitt's stars. And the distances I'm going to be talking about are 1,000 times bigger than the distance to the nearest galaxy. So not a few million years, but a few billion years into the past. And it's by measuring those distances, and as we'll see, the velocities, that you can trace out the history of cosmic expansion. So what about those velocities? Well, here's another astronomer in appropriate costume for observing. This is Vesto Melvin Slifer at the Lowell Observatory, and he's using a spectrograph, which is a tool for taking the light from a star and breaking it up, spreading it out into its constituent colors, into a spectrum. So here's embedded in the spectrum is important information about the chemical composition of the distant object, and also, it turns out, the motion. So stars are made of atoms. The atoms are the same as the ones on Earth, and the galaxies are made of stars. So when you take the light from a distant galaxy and you spread it out into a spectrum, you get something like the spectrum that you get from a star or like the sun itself. And I'll show you a representation of that. So here's a spectrum, and it turns out it's a little different from the colors of the rainbow. In addition to the continuum of light that you see here, there are these dark lines that cross the spectrum when you study it in the appropriate way. And those are the signature of atoms that are present in the atmosphere of the sun, of other stars, of other galaxies. And they turn out to be exactly the same as the atoms here on Earth. They obey exactly the same microscopic laws of quantum mechanics that set the energies at which they can emit or absorb light. So the atoms are the same, even when we observe them in distant objects. Now, you know what a scientist's job is. It's to take something beautiful, like the rainbow, and to turn it into a graph, as shown here. And so you can see that there are these little dips in the spectrum, which correspond to these black lines. They are the places where light is missing. Those are the places where the absorption has taken place. And it turns out that Slifer was able to show that for many of the galaxies that he could do back in the 1920s, the spectrum lines were the same ones that you saw in the stars, but they were shifted, and mostly shifted to longer wavelengths, to the red, as if the wavelengths had been stretched out, as if the object was going away from us. We're used to an effect like that, the Doppler effect for sound, where when a car goes by, you know it goes, As it's coming toward you, the pitch of the engine and the wheels is higher, and then it goes, If you're in the car, nothing changes. If you're in the car, you're just going, you drive by that person standing by the side of the road with their thumb out. You say, well, nothing to you. But the person standing there hears something change. They hear a change between the approach and the recession. And there is an analogous effect for light. It turns out the speed of light is 1,000,000 times bigger than the speed of sound. So you don't see approaching cars with blue headlights and receding cars with, well, you do, but there's a different reason for that. Okay. But if the speed of light were slow enough, you would see this Doppler effect. Slipher saw something that's like it for stretching out of the light from galaxies. And this was quite an interesting thing. It bubbled around in the astronomical community in the 1920s. And finally, in 1929, Hubble did what any scientist would do. He had two lists of numbers: distances to galaxies, which he'd measured from the brightness of those stars, and velocities, which Slipher had measured from the spectra. And Hubble plotted one against the other. He wasn't the first to do this, however. He called it figure 1, and we call it the Hubble diagram. This is velocity going up this way and distance out that way. Now, if you look at this, you can see a couple of things. One is the data is really terrible. You know, some of them are going fast, and some of them are going fast, and some of them are going slow at the same distance. Nevertheless, there is a trend in here. As you look at more and more distant objects, they're moving away from us more rapidly. As you look at more distant galaxies, they are moving away from our galaxy more rapidly. If you think for a minute, you might come up with this picture for what that means. This is the picture that I believe is in the mind of every Harvard undergraduate, and I'm certain every tenured member of the faculty, namely that they personally are at the center of the universe. And that the galaxies, somehow, knowing about this, are receding personally from you. This is what I call the egocentric universe. And if you think back to what I was talking about a minute ago when I said we've been demoted from our position at the center of the universe, this maybe would be a good time to apply that principle. So we're not at the center of the solar system. We're not at the center of the Milky Way, and it would be a kind of willful, blindness to the evidence, or at least the trend of things, to think that's yes, but somehow our galaxy is the special one, and we're somehow right at the center of things. So you might be puzzling, okay, things have just gotten worse, everything's moving away from us, but somehow they don't know that we're here. Right. My idea is this, that it's just, not my idea, the idea is this, that it's evidence for a universe that is expanding in all directions, every patch of it getting bigger over time, just like this animation, which I prepared at the greatest expense, where I took a picture, a Hubble Space Telescope picture, and then I just increased its size by the same fraction in each panel, and I showed those as an animation. So it looks like, how do I do this? Yeah, here we go. It looks like expansion away from that point. But there was nothing special about that point. It's just that I lined up all the pictures there. If I had lined up all the pictures anywhere else, it would have looked the same. What's more, if you look at it at the end, you can, whoa. Let's see. This is more complicated than I thought. Anyway, you can see that the ones nearby, the galaxies nearby, seem to be moving away slowly, where the ones farther away seem to be moving away more rapidly, and it literally does reproduce Hubble's diagram. Okay, so I now show you a picture of Edwin Hubble and Albert Einstein. You remember Einstein had gone to a lot of trouble to invent a theoretical model that was static, that did not expand. Here's Einstein visiting the Mount Wilson Observatory. Here's some very proud observatory directors and so on. Here's Edwin Hubble. You see he's being patted on the head by George Ellery Hale, the man who built the 100-inch telescope and the 200-inch telescope and the 60-inch telescope and the 40. He built the world's largest telescope 4 times. Anyway, he clearly approves of Hubble's work. And Einstein, at this point, gave up and said, well, okay, if the universe is expanding, and since I put in this cosmological constant to make it static, away with the cosmological constant. So here he is talking to De Sitter. He's in De Sitter's space, actually. And he says, get rid of the cosmological constant. If you go to the National Academy and you go to the statue of Einstein. If you climb up on his lap, which is now allowed and popular apparently, you can take a look at various equations that he brought down on this bronze tablet. This one says E equals mc squared. That's one everybody knows, has something to do with energy in the sun and, of course, nuclear weapons. Here's the equation for the photoelectric effect. That lies underneath the detectors that we have for light. And the equation at the top is the one that has the kind of pinnacle of mathematical intuition about the universe, is the fundamental equation for general relativity. And it has no lambda in it. That cosmological term, which he banished in the 1930s, is something which did not reappear by the time this statue was erected. Too bad, Albert. Okay, because we're going to need it later. So now what about the supernovae, and how do the supernovae help with this story? Well, these are stars which explode in a violent way, the way that Sterling Colgate and many of us find so thrilling. In this room, there are many people who study supernovae and the related stars that come before and after supernovae. Just for your benefit, I would like the people who are at the Center for Physics to raise their hand and hold it up for a minute. Come on, don't be shy. Now, for those of you who are not at the Center for Physics, the nearest physicist may be behind you. So I assure you, take a look around. If there are questions which you are too shy to ask me at the end, maybe you can ask your neighbor, and they will talk to you. Okay, but this is a kind of fanciful representation of a November night in 1572 when Tycho Brahe, the Danish astronomer, stepped out for dinner and noticed high in the sky where no star had been before, up there, a new star, which was a supernova in our own galaxy, the what we call today Tycho's supernova. And if you go to that spot today, not only was that thing bright and stayed bright for a long time, the riddles that Sterling wanted to unravel, not only was that true, but if you go there today, that is, if you take a look there today, with optical telescopes, radio telescopes, and X-ray telescopes, not available in Tycho's time, this is what you see. And there is the shredded remains of a star. From the Doppler shifts, we can see that this is expanding. This really is an explosion. And from the X-rays, we can see that the chemical elements that are present in this gas are different from the ones that are in most stars. This has a lot of iron in it. We think that the explosions are ones in which a dense nugget of a star, a white dwarf star, explodes to become mostly iron, and that the iron, this transformation releases a tremendous amount of energy that lights up this supernova and keeps it shining for a month or two very, very brightly. So that story seems to be more or less right when we go back with modern tools. And of course, this is not just, well, in my circles, we don't say not just of academic interest, because of course, anything that we're interested in is of academic interest. But this is of interest, ought to be of interest to you, I think, because the supernovae are very, and the lives of stars generally, are very directly connected to the world around us. The material world that we see in this room, the oxygen that you're breathing, the calcium that's in your bones, the iron that's in your blood, all of those elements were manufactured out of lighter elements, out of simpler elements, through the actions of stars, broadcast into the space between the stars by the exploding, by these explosions, and they become the material for the next generation of stars. So the atoms in this room literally were in stars before. A particularly poignant example is this car, which is 3,400 pounds of steel. And if you ask a naive person, where was it made, they might say Detroit. And they might say 1951. But the real story is, of course, that this was manufactured in supernovae that exploded before the sun formed, before the Earth formed, 5 billion years ago. And I think that makes it a more valuable car. Okay, What about these supernovae? What about distances? What about the accelerating universe? Well, here's a diagram that may look vaguely familiar. It's the same diagram as Hubble's diagram. It shows the velocity measured from the redshifts and the distance, in this case, judged from the brightness of supernova explosions. Here's the idea. If a supernova goes off, if they were all the same brightness, which is not quite true, but if they were all the same brightness, then the ones that appeared bright would be nearby. The ones that appeared dim would be far away. It's the same way you could judge the distance of a car from the brightness of its headlights. You might get fooled once in a while by, motorcycles or old Volkswagens with 6-volt systems, that sort of thing. But in general, you could tell which were nearby and which were far away from their apparent brightness. And that's what we've done here. So along this axis is the distance measured from the apparent brightness of the supernova. And each dot is a different supernova for which Saurabh Jha, who was one of my students, measured the properties of the supernova and the velocity that it was receding. One thing that's interesting here is that there's this little red square down here, which you may have noticed. That is the region covered by Hubble's original Hubble diagram. So you can see he had this phenomenon gripped by the toenail in very nearby. But it extends over quite an extensive distance. This is going out to about 2 billion light years and about 1/10 of the speed of light recession. And what I'm going to talk about is taking this farther and using it to see that the expansion has not been uniform, but has been changing over time. Okay, so if you want to see changes over big spans of time, you have to look at the back of the room. You have to look far away when the universe was young. You have to use the telescope as a kind of no-nonsense time machine to see the past. And here's the telescope we used for this work. This is the 4-meter telescope at Cerro Tololo in Chile. This is a picture taken with a digital camera with a silicon array. And so without a flash or anything, of course, you have the Milky Way here, the large and small Magellanic Clouds. The supernova 1987A went off in that big Magellanic Cloud. And we searched with this a camera on this telescope for distant supernovae. Here's how it works. Supernovae are very rare. As I said, the one from 1987 was the brightest one in 400 years. Then I showed you something about Tycho supernova. It turns out, taking into account all the pieces of the galaxy that we can't see, there's probably one every 100 years or so in a galaxy like ours. 100 years is a long time to wait. So if you ask a graduate student if they would kindly look at a galaxy every night and see if it was going to have a supernova, it would take them 100 years to do their thesis, and they would get bored. But the solution is, of course, to look at many galaxies. How many do you need? Well, if supernova is 1 in 100 years per galaxy, 100 years is a year is about 50 weeks, close enough. In France, of course, they have longer vacations, but in any case, about 5,000 weeks. So if you have 5,000 galaxies, your chances of having a supernova that's a week old or so are not so bad. And if you have more than that, then you can be pretty well assured of finding a supernova tonight. So you can take either of these strategies. The hard part is, though, the graduate students won't do that either. They won't look at 5,000 galaxies every night. They get bored very quickly. But what they will do is write a computer program. So here's Brian Schmidt telling his advisor how easy it's going to be to write the computer code that will find these supernovae. It will take images and subtract them and see the things that have changed. And more precisely, this was done at a time when there were 2 groups in the field. The other team had been working on their software, a couple of people, for about 5 years, let's say 10 man-years of work. And I said to Brian, well, how long do you think it'll take you? He said, well, I think I could do it in a month. It turned out this was not just youthful arrogance. It was true, sort of. He wrote software that crashed all the time, but he did do it in a month. But here's the idea. Here's the idea, and it's really simple. If you have an image a digital image, a picture, that is represented as numbers in a computer. And here's another one that you took last month, let's say. You can literally subtract one from the other and look at the difference. So we are looking for something new, something that changed, something that wasn't there. So this galaxy, although it's very conspicuous, a nice big spiral with some kind of other little fuzzy thing down there, is present in both pictures, and when you do the subtraction, it goes away. Whereas up here, there's something, and here there's something that might be the same thing or something different. It's a little hard to tell, but when you do the subtraction, it becomes clear in retrospect that there was, in addition to the fuzzy thing, the galaxy, there was a dot there, which was the star, which might well be one of the supernovae that you're interested in. So that's the idea, and that's what Brian brought to our team's work on finding distant supernovae to measure cosmic deceleration, as we thought it would be. We thought that the action of gravity over time would slow the expansion of the universe. So that means that if you look at distant supernovae, the light travels to you in an expanding universe. If the universe is slowing down while the light is in flight, that distance is not quite so big. The supernova will appear brighter. Conversely, if the universe were accelerating, who could believe such a thing, then while the light was in flight, the distance would expand a little extra. The light would have to travel farther, and the supernova would appear a little bit dimmer. So the game is to map out this relation between brightness and distance for supernovae, but supernovae that are far away. There's just one catch. Well, there are many catches, but I'll just tell you about one of them. And one of them is the universe is not clean. The galaxy is not clean. It is full of dust. And other galaxies are also full of dust. So that means when you observe one of these distant supernovae, you might be seeing it behind a screen of dust that you don't recognize very well. And if that happens, then the supernova will be a little bit dimmer, but not because the universe was accelerating. It will be, or because of its distance, but just because there was dust along the line of sight. So we thought about that, and what astronomers know is that when you see an object through dust, it absorbs the blue light more than the red light. So there's a change in color. And by measuring the color of the supernova, by measuring the color that you observed, you can infer, up to a point, how much dust there is along the line of sight. So another graduate student, here's Adam Rees, I believe this is on the day he got his PhD, standing in front of the old copper dome at, no, I'm not talking about Bill Press, at Harvard. That's what he did for his thesis, was to work out ways to use the measurements of color to figure out how much dust was along the line of sight. And this has become a whole cottage industry. So there were two groups in the field, and I just wanted to make the point that the Aspen Center for Physics was part of this discovery. Here is Brian Schmidt in the welterweight class and Saul Perlmutter in the lightweight class, boxing each other in front of a blackboard in the outside patio at the Center for Astrophysics, having what in diplomacy they would describe as a full and frank exchange of views. So there were two groups in the field. In 1997, later that fall, Adam Rees was analyzing our data, and being a graduate of the Massachusetts Institute of Technology, he knew that you have to keep a lab notebook. So here's his lab notebook, mildly illegible, but I have this big red arrow pointing to the place where he works out that the mass in the universe, remember that we were going to measure how much slowing down there was and infer how much mass, the mass of the universe is minus 0.36 in some units. It's the minus you should pay attention to. I said, Adam, that sounds crazy. You must have made a mistake. He said, well, perhaps. But he went back and worked on it again. Other people in the team verified this, and sure enough, the universe was not acting as if it was slowing down. It was acting as if it had negative mass, or in other terms, as if it had a cosmological constant or some springy thing that was an anti-gravity thing making the universe speed up. I won't bore you with the details of the analysis, just as I don't refer to other people's work too much. Along here, though, is this is a kind of diagram we like to make that shows how much dark matter, how much matter, gravitating stuff there has to be in the universe to match the supernova observations. And here's how much of the springy stuff, the cosmological constant or something else, there has to be. And what people guessed was that the value would be 0 and that this value would be 1. So what people guessed, if you punched a theoretical physicist in 1990 anyway, and asked them where did they think the universe would lie in this diagram, they would have pointed right there, and they would have given you an hour's worth of reasons why it had to do that. Well, okay. But what this shows is these big zeppelins of uncertainty show that both for our team, shown in solid, and their team, shown in dashes, that they both reveal a universe in which the value of dark energy, or the accelerating stuff, of 0 is very unlikely. You're much more likely to have something in which a universe that's speeding up than one that's slowing down. And what we've been doing in the past 20 years, of course, is measuring this better and better. And so what I'm showing you here is a more or less up-to-date compilation of the various measurements. Here's the supernova data. You can see that we've done a good job in shrinking these ellipses. We've got better data now and more of it. The green one has to do with galaxy clustering. This orangey one has to do with microwave background, the glow from the Big Bang, the fluctuations in the glow from the Big Bang. And when you put together all those bits of information, they zero in on a universe that is about 2/3 dark energy and about 1/3 of gravitating stuff, which is mostly dark matter. So this was quite a surprise to Einstein. Although he'd been dead for several decades, he had his picture on the cover of Science magazine, and you can see he was quite surprised. And not only that, he's carrying a sheaf of paper here with the Greek letter lambda on it, as though he had thought of it first, which is true, he did, but he rejected it. Anyway, it seemed very surprising to everyone. I'll show you a Hubble diagram and the effect of putting in some of this dark energy or cosmic acceleration so you can judge for yourself. So the points are the places, are the data, redshift and distance in astronomers' coordinates. This is a real grown-up plot, log. But what's happening here is this line is the prediction that you would make for different cases where you had a little dark energy or a lot. So 0 is no dark energy, and you can see that doesn't fit. You have to get up here, about 0.7, about 2/3 of the universe, in this funny form of stuff that makes the universe accelerate in order to fit the data. Okay, well, you don't have to take my word for it. The Swedes, who are very good at judging these things, awarded a prize to Saul Perlmutter and to Brian and to Adam. Here we are at the in the Grand Hotel in Stockholm, and you can see I am glowing with a halo of pride. And there are other people who were, it takes a village to win a Nobel Prize. Here's other people who are at the meeting. Alex Filipenko, where are you, Alex? He's in here. And Peter Garnovich are here, and many of these other folks. Where's Alex in the picture? There he is. There he is. Okay. Dressed up even more. Okay. So here's the idea. The picture is gravitating stuff about 1/4, dark energy, the accelerating stuff, about 3/4. Now, when a theorist shows this diagram, they are very proud. They say, look, the diagram is full. But you should always ask, what is it full of? And in this case, it's full of the most important thing in science. It's full of our ignorance. That is, we do not know what the dark energy is. And it turns out that the gravitating stuff is not mostly the atoms that I was referring to earlier that are lovingly made by the supernovae for our benefit. But it turns out atoms, the whole periodic table, and so on, is only about 4% of the universe. And that there's something else that's gravitating, for which we give this placeholder name, the cold dark matter, that is the rest of the gravitating stuff. Neither the dark matter nor the dark energy is firmly identified. We do not know what these things are. We have a good idea of the dark matter, and people are searching for it. If it's in the universe everywhere, it's in our galaxy. If it's in our galaxy, we're probably going through it like a car through a mist. And the front windshield ought to be getting mist on it. As the Earth goes around the sun and the sun goes around the center of the galaxy, we should have a wind, kind of a wind of dark matter particles going through us and going through the Earth and going through detectors which are capable of measuring the interactions with dark matter. So keep your eye on that space. The people who are doing the experiments believe that they will have a result within a year or two. Of course, they have had that belief for a decade or two, but we have a lot of confidence on that. The dark energy is much more mysterious. We do not know what it is. It could be Einstein's old cosmological constant, or it could be something that resembles it in giving a kind of springy quality to space itself, but not the same thing as the cosmological constant. Okay, I don't know how this diagram makes you feel. Some people feel very uneasy that, we're only the 4% part. But honestly, I think our slice of the pie diagram is the most interesting, that the baryons, the heavy particles, the things of the periodic table, interact in very interesting ways. The other parts we really don't know about very much. If they're interacting, we don't know anything about it. So maybe a metaphor will help you think about this, and then I'll open the floor for questions. So what about the dark matter? Well, we go out and we see galaxies in the universe. We see stars in those galaxies, and that's how we find out what's going on. And the presence of the dark matter is a lot like snow in the moonlight, which you get to study here in Aspen. And if you think about it, here's this image of mountains with snow on them. What you see is the snow. But most of what's there is the thing you don't see. It's the mountain. The mountain is not the snow. This is sounding more and more like a Zen koan. The mountain is not the snow, grasshopper. And so in the same way, the universe has bright lights in it, the stars and galaxies that we see, but they are showing us where the dark matter is, and that's the picture that we work with today. Similarly, if you go to the web and you look at conversations about dark energy and dark matter, they say things like, the scientists have no idea what the dark energy is. Well, that's true, but that doesn't mean we don't know that it's there. There are lots of things that are like that. So here's an image of what you would think of wind in the trees. But you don't see the wind. You only see in fact, you don't even see the effect of the wind. You see the effect of the wind as represented by a painter. You see the effect of the wind, which is the swaying of the branches. What we see is the accelerating expansion of the universe. What we infer is the presence of this dark energy. And so even though we don't know its precise nature, we know that it's there. We know that it's acting. Okay, well, I could go on much longer, and I have under other circumstances. But I think this is a lively audience, and I would definitely like to have your questions. So I would just like to say, if you want to learn more about this, I couldn't recommend a better book than this one, which is available translated into several languages. Thank you very much. Okay, now I'm ready to answer your questions. Yes?
Is it possible that the star of Bethlehem was a supernova, and if so, can scientists still see it with these super?
Yeah, it's an interesting question. Could the star of Bethlehem have been a supernova? It certainly was, reported as a bright thing that you could follow and would take you in the right direction and so on. And people have looked for historical supernovae for which there might be other records, say in Chinese records and so on, in that era. There doesn't seem to be a likely candidate that is a genuine supernova. There may have been some other astronomical phenomenon. It could have been a conjunction of planets and so on. So, but there is there's no supernova that we know about that would be within, a few years of 2014 ago. Well, I was exaggerating a little bit, or what's the opposite of exaggerating? I was underplaying, I was understating it. The supernova fades by a factor of 2 or 5 in a month. But it keeps shining for quite some long time. So Tycho's supernova, the one that the Chinese recorded that we associate with the Crab Nebula from 1054, was seen in the daytime, was seen for many months after the explosion. So we believe, and we're pretty sure that we understand well enough, that there's radioactivity that is produced by the elements that are created in the explosion itself, and it's the glow is the decay of those isotopes as they power the supernova at later times. So this study that Sterling Colgate did, where he worked on nuclear weapons and also worked on stars, turns out part of the story of how those stars glow has to do with the synthesis, easy to say, synthesis of new and unstable elements in an explosion. Yeah?
I gather there's a supernova currently in the Whirlpool galaxy. Is there anything novel about it, or are we learning anything about it?
There are a lot of experts here about the supernova in the Whirlpool galaxy. This is 2011 FE, as we call it. The wonderful thing about this is that the supernova searches have advanced beyond the point that I was talking about. So instead of searching just every night, some of the searches are searching more frequently. Some of them are doing a good job of autonomously detecting the event. So I showed you the thing with the subtraction and said, you know, you could look at that and see it. But you could also teach a computer to do it with some difficulty. And it turns out that these things, many people have been working on this, and it has been successful, and it has been applied, was applied, in that case in 2011. And the thing that came out of that, one thing that came out of that that's very interesting, is that they saw that the supernova, they caught the supernova very early, and so they have very strong constraints on what the star was like at the moment of explosion, or very nearly at the moment of explosion. So you heard Sterling asking a bunch of questions, you know, what he wanted to know. One of the things we want to know is what kind of star blows up. The most popular picture in the past has been that there's a white dwarf and that there is gas that comes from another star onto the white dwarf and that pushes it to the point where it ignites. But in that case, you ought from time to time to see that other star. And in this case, for 2011 FE, with the constraints that have been put on the companion are very stringent. And for that and other reasons, people have been looking at other models, ones in which there might be two white dwarfs that collide with one another, one way or another. So it's been very important in kind of providing the best test we've had so far of the basic picture for what those explosions are. And our basic picture was not confirmed by that test. It doesn't mean it's wrong, but it does mean that other possibilities are open. So we learned a lot. Yeah?
If the heavy elements of the fluid occurred 5 billion years ago,
Yeah.
and supernovas are somewhat infrequent,
Yes.
the whole game is only 13 billion years old.
Yes.
It doesn't seem like there was enough of them to make all the values.
Boy, you should have come to the lecture at 3 o'clock this afternoon, where we heard all about how how the stars, people have worked this out. You know, if you had star formation in the amount that we think has taken place, could it make the elements that we see are present? So people have really thought about this question. The one thing that is not so obvious about it is that the rate of star formation in the universe and in our galaxy was higher in the past. So our galaxy was forming stars more rapidly in the distant past than recently. So that chemical enrichment seems to have been very rapid and built up from a very low level to a level about the level of the sun, which is a sample from the time the sun formed, almost 5 billion years ago, to that value. So one of the most illuminating things, of course, is to look at the oldest stars, which have the least heavy elements, because they might have evidence of just one event, or two events, or a small number of events anyway. And by looking at those oldest stars, and there are people who've come to this workshop who are really experts in that, you can begin to understand better this mechanism of enrichment. But the short answer, which I didn't give you, is that the numbers seem to work out okay. Yeah. Gee. Oh, sorry. I just get the message so quickly from you. Yeah, go ahead.
I was confused by Einstein's statement. With lambda, is the same equation true today, but lambda is now a variable?
Yeah, so the question was, I was confused by Einstein's statement. You can always get away with that. I was confused by Einstein's statement, you know, that he had put in this cosmological term, and then I showed you that equation. You didn't really get a chance to look at it. But there is one way to think about the cosmological constant is as if empty space itself has a kind of energy associated with it. And in Einstein's theory of gravity, different from Newton's, the presence of pressure or energy in a place contributes to the gravitation. So that's kind of funny. When you talk about the Earth moving around the sun, you know, you get the mass of the sun. There's nothing in there about the temperature of the sun or the pressure of the sun. It's just the mass. Newton's theory is like that. Einstein's theory includes the contribution to the warping of space, which is the part of his geometrical theory, that comes from the presence of both matter and energy in the universe. And so if there's this funny kind of, that's why we call it dark energy, if it's a funny kind of energy that contributes, only in this negative way, to not attraction but repulsion, but nevertheless using the same mathematical framework, that's the idea. So if that's true, then what we're saying is the space doesn't act as though it has no properties. A vacuum is not an empty, featureless place. It's a place that has associated with it this background energy, could be. And you know, the quantum picture of the vacuum is not that it's a featureless nothing. It's that there are particles and there are antiparticles being formed and annihilating all the time. That quantum picture of the world is something that seems to be right, and it's righter than, you know, a world where that doesn't happen. For gravity, we don't have a proper quantum theory of gravity, and so we don't quite know how to talk about all this. But it looks like Einstein's approach, which was to talk about the cosmological constant as something that would affect the equations of general relativity, is certainly a very good approach, and that's what most people are following now.
By quasi-static, you meant that lambda was set such that it wasn't expanding or...
That's right. He meant that the universe was more or less static. The stars were not moving out or moving in rapidly. Okay, I can see you're conferring on this question. That's allowed.
Yes. Well, actually, we do have a couple questions. One thing that I wanted to ask you was, is it possible that there's an association between the dark energy and like quantized, like time was quantized, and there was some evolution of forces, you know, at the creation of the universe? Would that then eliminate the concept of t minus 0?
Well, I'm not sure I understand your question exactly, but let me answer the part of it I do understand, which is the piece, if gravity is, we assume that our goal is to treat all the forces of nature in the same way. And this was Einstein's dream, was to have all the forces of nature somehow treated in the same way. In modern terms, that would mean that the gravity would have to be treated like the other forces, the strong, the weak, and the electromagnetic forces. And there is a unified theory for those three forces, which is very good and works extremely well. But gravity's been hard to include in that. The approach that people have taken, in which gravity fits most naturally into the picture of all the forces, It comes from string theory. And there are some versions of that where gravity seems quite naturally to be part of this rather complicated mathematical story. Now, whether that's the way we'll eventually come to understand gravity or not, I don't know. But I think your intuition is right that understanding gravity is very, very important, and it's more important about understanding the origin of the universe, the early times in the universe. And when the time is short, when the scales are small, when the energies are high, that's when understanding gravity fully would be more important. Yeah?
Could you talk a little bit about the nuclear reaction that takes place when a supernova explodes? What do they take?
Yes, good. So there are different kinds of supernovae. Some of them are powered by gravity, where the core collapses, and it's mostly gravitational energy when the thing bounces that blasts the star apart. That's what Sterling was talking about, those calculations that kept failing and so on. Another kind of explosion is the kind that takes place in a little dense nugget of a star, the thing that's left over after a star is burned out, a star like the sun burns out, the thing we call a white dwarf. It's very dense, and there's been nuclear fusion that's taken hydrogen into helium and helium into carbon and oxygen, so that the core of the star, this little dense core, about the size of the Earth, but with the mass of the sun. So, you know, a teaspoon full of it would weigh more than a rhinoceros. I mean, this would be funny stuff. Anyway, this white dwarf, the very dense star, if it's left alone, it'll just cool off. And we see white dwarfs that are, I don't want to insult anybody, but, you know, they really are the dullest stars. There are people who love them, I know, but they're very quiet. They just cool off. They don't generate any. But they, if they're in the wrong neighborhood, they might have a neighbor who puts mass on them, or they might have a collision with a neighbor that would lead to the ignition of the carbon in the core. So the principal picture we have is that the carbon will start to burn. It's not burning like burning coal, where you combine oxygen and carbon and, you know, make carbon dioxide. This is nuclear fusion of carbon, and it would heat the center very rapidly and make a flame of nuclear burning that would go out through the star like a bomb.
So you think it's carbon 12 plus carbon 12 forming magnesium?
Yeah, and on up, all the way up to iron. Iron's the most tightly bound nucleus, and we think that these stars make about half a solar mass of iron, and that's the stuff that powers the light curve and that we see that makes these things so bright. And it could be that the fact that the range of masses for these white dwarfs when they explode is not too big is what makes these stars so uniform and so useful for this distance measuring that I described today. Somebody, yes, go ahead.
Do you know what rate the universe is expanding?
Yes, I do, but it's in our units. It's expanding at 73 kilometers per second per megaparsec, more or less. But, you know, that might not mean much to you. But the right way to say it is that it is expanding at a rate that would get it to its present size in 14 billion years. That's actually more helpful. It means it's expanding by 1/14 billionth each year, more or less, if it's just coasting along. So the distance from here to some middle distance galaxy is growing every year by a part in 14 billion, roughly speaking. If the universe is speeding up or slowing down, you have to take that into account. All this business about the light traveling from one place to another, you better take that into account. But roughly speaking, that's not a bad way to think about it. So it's a fractional change, and the fractional change is like 1 over the age. It's about 1/14 billionth per year.
They haven't figured out in terms of speed of light or...
Well, you can see objects moving away from us we see actual physical objects moving away from us up to well over 95% of the speed of light, and we see the cosmic microwave background, which is redshifted by a factor of 1,000. So we see stuff that is going practically at the speed of light, that's for sure. Yeah?
So we know that our universe is finite.
Our universe. Go ahead.
We know that it is finite. Yes, exactly. But so we know that it is finite in time, right? 13.8 billion years.
Yeah.
And we can't see past a certain point.
Right. It's kind of foggy.
But do you think that either there's an edge or that it's infinite in space?
Right. So the question is Is there an edge, or is it infinite in space? Well, the picture I'm talking about would be infinite in space and finite in time. I thought you were going to ask something a little more tricky about whether ours is the only universe, but I'll leave that to others. Okay. Yeah. All right. Sure. Just a couple more.
Isn't dark matter just another name for the ether?
No.
And the ether you're looking for is turning with the Earth. It wouldn't be passing through the windshield. It would be the windshield.
The dark matter we're looking for is what we think would be non-interacting, just gravitating stuff. We know that it's present in the galaxy because we see their rotation curves and so on. It's not just a name for the ether, which was sort of a medium through which electromagnetic radiation would travel. These things, yeah, these things don't need that, and light doesn't need that either. But yeah, well, okay. The nature of it, well, okay, so the picture we're trying to test is that it's non-interacting particles, presumably subatomic particles of some type that we don't quite know yet, but that might resemble neutrinos, but they can't be the neutrinos because they have slight mass. But there are plenty of other particles people have thought of, but not discovered yet. So, I mean, you're right to point out that this is in the realm of uncertainty, and it's at the edge of knowledge, that's for sure. And I guess we'll just have to wait and see if we can get more evidence on the presence of the dark matter. Yeah?
Why, if any, is the problem for us on Earth with this expansion?
Is it a problem for us? Well, first of all, I think people really want to know. Right? I think we want to know where we came from, where we are, where we're going. And this is a new conception in which if the universe is accelerating, I've only talked about looking into the past, but you might want to think about the future. If it's accelerating, then as time goes by, it will expand faster and faster. It will be literally exponential if it's the cosmological constant. That means that as time goes by, the fraction of the universe from which light could have reached us will be smaller, that we will have fewer and fewer galaxies that we can see, and that eventually it'll just be us and Andromeda is going to hit us. So I don't know if that apocalyptic vision of the future is enough to make you think, should I check my homeowner's insurance? But I think this question of sort of, what is our fate, where are we going, is something that people are interested in, and that I think it's fair to say that our current knowledge of the dark energy is so limited that we can't honestly predict whether we'll have this exponential expansion or some other future for the universe. But it does say that if we don't hurry up and make the measurements now, we'll never know. So this is a good argument for funding astronomy now. I think it would be the right thing to stop now so that people can leave politely if they wish. I'll be around for a while, and you saw your nearest astrophysicist earlier, so you can buttonhole them. I'm sure they'll be happy to tell you about their work.
Support for this grassroots community television program comes from U.S. Trust. From wealth structuring to investment management, U.S. Trust's global perspective, unique team approach, fiduciary platform, and more than 200 years of experience provide for the kind of insights, solutions, and expertise that have a worth all their own.